Hi there, my name is Colin and I'll be your instructor for today. We're going to learn about some advanced integration techniques. Recall the product, quotient and chain rules of differentiation, each of which is used to differentiate a particular type of function. For instance, the chain rule is used to differentiate a composite function, otherwise known as a function of a function. Well, it turns out that for integration, there is a technique called integration by substitution, which is used to integrate a function of a particular type. Now overall, the purpose of integration by substitution is to transform a difficult integral into an equivalent but simpler one, expressed in terms of a new variable. So, what exactly is integration by substitution? Recall the chain rule for differentiation from day 2, which is used to differentiate composite functions. And recall that the rule can be expressed in the following functional notation, where g is defined to be the inside function nested within the outside function f. The basic integration by substitution formula is obtained by integrating both sides of this formula with respect to x. Therefore, integration by substitution can be essentially thought of as the chain rule applied in reverse. For example, if we differentiate the composite function sine of x cubed plus 1, we get 3x squared times the cosine of x cubed plus 1 by the chain rule. The reversal process of integrating both sides with respect to x then recovers the original function. So, what types of functions are amenable to the technique of integration by substitution? Firstly, note that the formula above can be slightly rephrased as the following, where f of g of x is some composite function, and capital F is the primitive or antiderivative of the outside function f. Therefore, it can be concluded that the method of integration by substitution is typically used to integrate any composite function that happens to be multiplied by the derivative of its inner function. Now that we've dealt with what the technique is and when we typically use it, let us now learn how to apply it in practice. The method, which shall be demonstrated on an example integral and explained in a series of concrete steps, involves employing what is called a change of variables to transform the difficult original integral into a simpler one. You may perhaps find this procedure to be quite lengthy at first, but we'll get the hang of it through sufficient practice. Suppose we wish to use substitution to integrate the function 3x squared times the cosine of x cubed plus 1. Note that the function we're integrating is indeed amenable to the method of substitution. That is, we have a composite function that's multiplied by the derivative of its inner function. Now, the first step is to set our substitution u. Identifying the composite function to be the cosine of x cubed plus 1, we define a new variable u to be its inner function, x cubed plus 1. The second step is to change the variables. Since u is equal to x cubed plus 1, we then differentiate u with respect to x, giving 3x squared. We then treat du dx equals 3x squared as an equation and make dx the subject. Substituting our expressions for u and dx into our original integral, we obtain the following. Which then simplifies to the simple integral cosine u. We have thus transformed our original integral, expressed in terms of the variable x, into an equivalent but ultimately simpler integral expressed in terms of the new variable u. Evaluating the new integral with respect to u, we obtain sine u plus our constant of integration c. Now, since u was just a temporary variable used to help us evaluate our original integral, which was in terms of x, the final answer must therefore be in terms of x. Therefore, substituting x cubed plus 1 back for u, the final answer is the sine of x squared plus 1, plus our constant of integration. Let us summarize the technique. We first identified our substitution u to be x cubed plus 1. Differentiating u with respect to x, we subsequently obtained dx to be the following. This, along with our substitution, was then used to transform our original integral into an equivalent but simpler integral expressed in terms of u. We then evaluated this u integral before transforming the answer back in terms of our original variable x. Here's another example. Consider the following integral. Since the composite function within the integrand is the square root of 1 plus x squared, we therefore set u to be its inner function, 1 plus x squared. Differentiating u with respect to x, we then make dx the subject. Substituting u and dx into our original integral, we then obtain the equivalent but simpler integral in terms of u. Evaluating this new integral, we get the following. Before writing our answer in terms of our original variable x. Alright, it's time to pause the module and have a go at these following practice questions. Here are the answers to the practice questions. And finally, here's a summary of what we've learnt in this module.